All right. Good morning, everyone, and welcome to our last day of class. Um, so, what is happening in our class? Well, this afternoon, the final exam is going to be posted. Um, it'll be cumulative, so going back all the way to truth tables and logical equivalences. It will be due Friday by midnight. Also, this morning, I posted an extra credit assignment that will be going towards the final exam. Um, it's a lot of the newer material, which didn't show up on any homeworks, and the material we're talking about today won't be on the final. Um, there is a bunch of it in the extra credit, so if you want to take a crack at it, go for it. But also today, what we'll kind of be focusing is on how this last topic, which is what makes up chapter 8 of the textbook, is kind of a big application of a lot of what we've been talking about. In particular, a lot of what was talked about in the chapter on functions. Um, so, right, I guess, yeah, administrative stuff, the final, and the extra credit. The extra credit isn't due until Monday, so if you want to put that off until the weekend, you can do that. If you want to focus on our final or whatever else you have going on during this finals week. So what I want to talk about is the chapter is called Infinite Sets. And I think a motivating example behind the first definition is, before we really get to the notes we'll be going through, is suppose that you and your sibling are young and it was Halloween. You went trick-or-treating, you got a pretty good haul, but then your parents take your candy and combine it and then split it up evenly between the two of you. So they're trying to be fair, make sure everyone gets the same amount of candy, but you and your sibling want to make sure that you actually got the same amount of candy. The problem is you and your sibling are pretty young, you can't count very high. You did a good job getting candy. So the question is, you have two piles of candy. How can you tell that there's the same amount of candy in the piles if you don't know how to count them? Which is kind of an interesting question and maybe not clear what you do. Because you can't just say take one pile, count it, there's 50, take the other pile, count it, there's 52, and so they're not the same. You don't know how to count them, but you want to somehow figure out if they have the same amount. So one way to do this is each of you takes a candy from your pile and kind of matches them up. Then you take a second piece from your piles and match them up, and a third one and match them up. So you're kind of going one for one on the candies, and if you match them up perfectly and you end up and you stop at the same time, then you have the same amount, because every one of your candies gets matched with one of your siblings' candies, and every one of your siblings' candies got matched with exactly one of your candies. So there's this matching of them, and even if you don't know how many there are, you didn't count them, you know that there's the same amount. And so that's a way of telling when things have the same size without actually counting. And another way of describing what you did, which children would definitely not have, but we do, is you constructed a bijection between one pile of candy and the other pile of candy. So the function which takes one candy and sends it to the thing it got paired to, that's a function. It's 1-to-1 because different candies in one pile get paired with different candies in the other pile. and it's onto because every candy from the second pile was paired with something in the first pile. So this is the idea, and now we'll kind of get to the math here. This is the idea that we're going to use. If we want to say that two sets have the same size without just counting them, the word that we'll use is equinumerous. We'll write this little tilde here. A is equinumerous to B, and what this word will mean is that there's a bijection between A and B. So these are our two piles of candies, and they are equinumerous if there's a bijection between them. And so the way that we will think of this is if there's a bijection from one set to another set, those sets have the same size. But what we'll see as we go through the different kind of results today, a lot of it will be examples with a couple of proofs thrown in. We'll see that for finite sets, this idea of having the same size being there's a bijection, for finite sets, this works like we think it should. But what we will also see is when you're talking about infinite sets, there's a lot of kind of strange behavior. And the resolution, the conclusion we come to when we see this strange behavior is not that there's anything wrong with this definition. This definition, which is the existence of a bijection, is the way we'll talk about sets having the same size. This is a good one. Just infinite sets are very different than finite sets. They have very different properties, and we have a lot of different examples which you just can't reproduce with finite sets. What we also want to do is we want to be very careful about what we mean by infinite and finite. So part of rigorously defining what it means to kind of be equinumerous, which we're taking as our formalization of having the same size, we also want to be careful about exactly what we mean by saying something is finite, which everyone here, if I wrote down some sets, you could say this one's infinite, this one's finite. But we want to be really explicit about what we mean. What are you checking when you say something is finite? So to distinguish between these sizes, we'll first say if you take a natural number, I sub n is all the numbers between 1 and n. So I sub n is the numbers 1, 2, 3, and so on up to n. As a sort of quirk of this, I0 is the empty set. There are no numbers greater than 1 and less than 0. So if you write down I0, there's nothing in there. And so what we mean when we say a set is finite is that a set is finite if it is equinumerous to one of these sets. And we'll say that a set is infinite if it's not finite, if it's not equinumerous to any of these sets. So what this suggests is proving something is finite is actually kind of complicated. We have an intuitive idea, but this says no matter which one of these sets you look at, and no matter what function you try, you won't find a bijection. And putting it in that way, saying one of these sets for any n, and you can try any function you want from any one of these to your set, and it's not going to be a bijection. That's actually a really complicated statement and not at all clear how you would prove that. So before we get into really talking about infinite and finite, let's just look at some examples of sets which are equinumerous. So like I said, the finite case, things are as we would expect. If we take the set 1, 3, 5, 7, that is equinumerous to 1, 2, 3, 4. This is an example of one of these i's. 1, 2, 3, 4 is the set I4. How we can prove this, remembering this tilde means there's a bijection, is for finite sets. If you have them explicitly written out, you can actually write down the bijection. So the bijection, 1 goes to 1, 3 goes to 2, 5 goes to 3, 7 goes to 4. So matching them up in the kind of first one goes to the first one, second to the second, and so on. So for these explicit finite sets, we can actually write down a bijection. And you can check, well, this is a function because every input appears once. It's 1 to 1 because if you take any two inputs, they have different outputs. And it's onto because 1, 2, 3, 4, each of those appears in the range. So these sets are equinumerous. And then from this definition, we can say that 1, 3, 5, 7 is finite, which is what we would expect, but we've shown that from the careful definitions we've laid out. When we start talking about infinite sets, things get more complicated. So as a first example, let's see, well, this one is not so strange looking. What the second example says, if you take the set of even numbers, so 2n for n in the integers, so positive and negative even numbers. And then if we look at the odd numbers, 2n plus 1, which is the integers minus the even numbers, those sets are equinumerous. So the even numbers are equinumerous to the odd numbers. And if we want to show this, if we want to verify that these sets are equinumerous, that means write down a function and show it's a bijection. And the way we can do that is we'll define a function from the even numbers to the odd numbers by sending an even number to its next number. So this picture is looking like we have an even number, it goes to the odd number. We have an even number that goes to its odd number. And so here's a function sending even numbers to odd numbers, but we want to check that this is a bijection. So if you take an odd number, well, go to the even number right before it, and that even number is sent to this odd number. So it is onto. Every odd number is the image of some even number. And we know it's actually the number right before it. This is also 1 to 1, because if you have two inputs, 2n and 2m, that gets sent to the same place, well, that means that f of 2n, our function says that is the odd number right after it. F of 2m is the odd number right after that. And if these two odd numbers are equal, then subtracting 1, we get that 2n equals 2m. So the inputs we started with were the same. So this says, with our kind of intuitive interpretation, there are the same number of even numbers as there are odd numbers. And that's kind of not surprising. What I think is more surprising is the even numbers are equinumerous to the integers. The way that we can do this is we need to define a bijection, let's say from the integers to the even numbers. And what we do is say that take an integer, multiply it by 2, and that takes any integer and assigns it an even number. This is also a bijection, because if you have an even number, it is the image of n. So 2 times n is an even number. Then applying the function to this n here is how you can get 2 times n. To show it's 1-to-1, if you assume that you have two numbers whose outputs are the same, then that means that 2n and 2m are equal, but dividing both sides by 2 gets us that n and m are equal. So a big part of this first first understanding what equinumerous means is really you're showing a lot of things are bijections. And that's something that we at least have done before. So given this function, showing it as a bijection is not difficult. What is kind of weird is that this is saying that even numbers and all the integers have the same size. But that seems really weird because the integers, so this is saying you take the integers, you throw out all the odd numbers to get just the even ones left, and those things have the same size. So this is where having the same size, or at least this way of defining having the same size being equinumerous, there being a bijection, is a little counterintuitive, because you are inclined to say the even numbers are much smaller than the integers, because there are a lot of integers which aren't even numbers. But according to this definition and this short proof here, they are equinumerous. We can match them up in this bijective way, with every integer being paired with 2 times that integer, and that pairs up every even integer with with any integer at all. To keep the kind of strange examples going, the integers are equinumerous to the natural numbers. So here this is saying if you start at 0 and go up, you have the same number of things as if you included all the negative numbers too. So I won't walk through this, but in what this is, the way to interpret this function is this takes an integer and the negative numbers get sent to the even numbers, and the positive numbers get sent to the odd numbers. So that way of pairing it up gives you a bijection. Looking at this proof, showing it's onto means given any natural number, if it's even, it was mapped to by a negative number. If it was odd, it was mapped to by a positive number. And we can also show this is 1-to-1, because the individual parts are 1-to-1, and they're being used on separate parts of the integers. So this is also strange by saying if you start with the integers, you throw out all the negative numbers to get the natural numbers, you end up with a set of the same size. Which again is strange because n is a proper subset of the integers. There are a lot of integers which aren't natural numbers, but at least according to our definition, they have the same size. There are some other examples too. So for instance, if we take the interval 0, 1 and the interval 1, 2, We can define a bijection by saying, take an x in 0, 1 and send it to x plus 1 in 1, 2. So here this is, the picture is saying take 0, 1 and shift it right 1, and it'll land on top of 1, 2. So this map is, first of all, a function into 1, 2, because if you start with something between 0, 1, and you add 1 to everything, you end up between 1 and 2. It's 1 to 1 because if x plus 1 and y plus 1 are equal, then subtracting 1, x has to equal y. And it's onto because if you have something between 1 and 2, if you subtract 1 from that, you get to be in 0, 1, and that subtracted number is the thing that gets mapped to the y you started with. So this is maybe back to the not too surprising place. This interval of length 1 is equinumerous to this interval of length 1 also. But we can have stranger examples. The interval 0, 1 is equinumerous to 0, 2. The bijection that works is f of x equals 2x. You can show this as bijection kind of combining this example 5 and also with some of what happened in this example 3. So this is a bijection, but now we're saying that this interval of length 1 has the same size as this interval of length 2, which is again counterintuitive because this is longer, it should have more things in it. But what we're seeing is infinite sets. As far as size goes, some things are unexpected. And in fact, 0, 1 is equinumerous to every interval AB, every finite interval AB. Because we can come up with a specific bijection. This is a line which essentially takes, well, it takes 0, 1 and it stretches and shifts it so it lands on top of AB. So in this example 5, we shifted. In example 6, we stretched. You can do that in general for any interval. So this is saying any finite interval is equinumerous to 0, 1, because we can find a bijection that does that. But things get even crazier. Using a more exotic function, tangent, tangent is a bijection from negative pi over 2 to pi over 2 to the real numbers. So remembering the graph of tangent, that is something like this with asymptotes at negative pi over 2 here and pi over 2 here. Tangent is a bijection. It has an inverse function, or tangent restricted to this range has an inverse function, arctangent. So it's a bijection. So this is things getting even weirder. This finite interval is equinumerous to all of the real numbers. But if we're going to go with bijections or the way of saying that sets have the same size, we're stuck with this, and we just chalk it up to infinite things are weird. Another example, which kind of along the same lines, is e to the x. So its graph, remember, is something like this. This is a bijection from the real numbers to 0, infinity. Because it goes all the way down, it has an asymptote here, so it doesn't make it to 0, and it goes all the way up, and its domain is all the real numbers. So here we again, if we take the real numbers and we throw out half of them, we end up with a set of the same size. So there are, so we have these specific results. We also want to talk about combining them. And we can combine them really using things that we've already proved, just restated in this equinumerous terminology. So if you have sets A, B, and C, A is equinumerous to A. If A is equinumerous to B, then B is equinumerous to A. And if A is equinumerous to B and B is equinumerous to C, then A is equinumerous to C. And in these cases, we can use facts that we've established about bijections. For the first one, the identity map, which sends everything to itself, is a bijection. And the existence of this bijection says that A is equinumerous to A. For B, if you have a bijection one way, which is what this assumption says, if they are equinumerous, that means there is a bijection. We know that if you have a bijection, its inverse is also a bijection. And that means we have a bijection going the other way. So B is equinumerous to A. In C, our assumptions say there are two bijections, F from A to B, G from B to C. And one fact we proved was that if you have two bijections, the composition is also a bijection, now going from A to C, which means that A is equinumerous to C. So part of a way we can interpret this is that in some sense, being equinumerous is like an equivalence relation. This looks like we're saying it's reflexive, and this is symmetric, and this is transitive. We don't use that terminology though, because equivalence relations live on a set, and there is no set of all sets. That's an object which doesn't make sense. Or we can't say that it is a set. But that's what these properties look like. So kind of what we're saying is, if you group sets by being equinumerous to each other, you're kind of getting equivalence classes where things in the same class you think of as having the same size. And if we look back and combine some of these results here, so for instance, we said that the even numbers are equinumerous to Z and Z is equinumerous to N. So that means that the even numbers are equinumerous to N. In these other examples, this example 7 can say that every finite interval is equinumerous to every other finite interval. Because you take an interval AB, it's the same size as 0, 1, and that's the same size as some CD. But also, 8 and 9 are saying every finite interval is equinumerous to R, because you can go your interval to negative pi over 2 to pi over 2, and that to R. And also all of those finite intervals are equinumerous to 0 to infinity. So what we end up seeing is that for a lot of kind of common sets, there are two big equivalence classes. All the finite intervals and the real numbers and this half line, those are all equinumerous to each other. There are also a bunch of things which are equinumerous to the natural numbers. And that leads to a definition which is essentially saying, are you equinumerous to N or not? So say that a set is denumerable if it is equinumerous to N, and say it is countable if it's finite or denumerable. And a set is uncountable if it's not countable. So what we've seen up here is things like the integers and a set of natural numbers. Those are all denumerable because we can find bijections with n. And countable says you are the same size as the natural numbers or you're finite. What we haven't seen so far is where do, say, the real numbers go? I didn't give you a bijection between the natural numbers and real numbers, but that doesn't mean there isn't one. And this is kind of a tough question. How do you say that no matter what function you try, from the natural numbers to the real numbers, you will never find a bijection? So that's kind of difficult. So to try to get there, the chapter proceeds by establishing some more facts about being equinumerous. So some of them are other ways of combining bijections. So this first one says, if A is equinumerous to B and C is equinumerous to D, then A times C is equinumerous to B times D. So this proof is saying if you have a bijection from A to B and one from C to D, you can find another bijection from A times C to B times D. And the idea of the proof is you have something in A times C, where do you send it to? Well, the assumptions say you have a function that takes things in A and sends them to things in B. You have G, which sends things in C to things in D. So if you have a pair, which comes from A and C, use the two bijections to send it to the corresponding elements of B and D. So what the bijection turns out to be is that you take a pair XY, X is in A, so apply F to it. Y is in C, so apply G to it. And that gets you into B times D. And you can check that that turns out to be a bijection. Another way of constructing bijections is if you have two pairs of sets, A equinumerous to B, C equinumerous to D, and A and C and B and D are disjoint, then their unions are also equinumerous. With the function being, take something in A union C. If it's in A, apply F, because F sends things from A to B. If you have something in C, apply G to it, because G sends things from C to D. And this works. You're pairing up the A half with the B half, the C half with the D half, and because they're disjoint, this pairing up actually works. So beyond talking about these general facts, we also want to get into more specifics of these different sizes of sets. So they're really finite sets, denumerable or countably infinite sets, and then there are these uncountable sets. In the realm of finite sets, this size stuff works like you think it should. What takes a little bit of work at first is that being finite means you're equinumerous to some in, but what isn't included in that is you're equinumerous to at most one of them, because we'd like to talk about the size of a finite set, but from the definition, it's not clear that you have a unique size. And this is kind of a test for our definition. If we're saying sets have the same size, there's a bijection, finite sets need a single numerical size, and it should match the in that they are equinumerous to. And it turns out that you're able to do that. It does take some proof, There's a full version of these notes which actually does that, goes through that, and it takes like a page. But for a finite set A, we can talk about the cardinality of A, and that is the unique natural number, so In is equinumerous to A. So this is good because it matches with how we think finite sets should work. But also, this is good because now when you're talking about finite sets, you have access to proof by induction. Because you can say, suppose, so how induction would work would be, first, prove things are true for sets of size 0, or maybe sets of size 1, and the inductive step would say, assume I know whatever I'm trying to prove is true for sets of size n. Use that to prove that something is true for sets of size n1, or n plus 1. So an example of that is this theorem here. So this theorem says if A is finite and B is a subset, then B is finite, which is what we think should happen. More specifically, if A has cardinality n and B is a subset, then the cardinality of B is less than or equal to n, and unless it is all of A, it actually has a smaller cardinality. So this is how finite sizes should work. If you take a part of your set, it has a smaller size than the whole. And this proof can proceed by induction. So we are proving for all natural numbers n this statement. If A has size n and B is a subset of A, then B is finite and the cardinality of B is a subset, is less than or equal to n. So proofs by induction have two cases. First, assume n equals 0. So that means so what we need to prove is that if the cardinality of A is 0 and B is a subset of A, then B is finite and B also has cardinality less than or equal to 0. But what we can prove is that, or kind of what we know is that if the cardinality of A is 0, then it has no elements, so it's actually the empty set. The only way of being a subset of the empty set is to also be the empty set. And this set is finite and has cardinality 0. Because this is exactly what we called I0. In the inductive step, we pick some n greater than or equal to 0 and assume that this property so we are assuming this is true for the n that we picked. Then we want to show that it's true for the next number. So we have this blue underlined fact as our assumption, and then assume we have a set of size n plus 1, and B is a subset of it. So if B is equal to A, then by our assumption, or what this A looks like, B is also finite and has cardinality n plus 1 because it's the same set as A. If B isn't equal to A, then we can find an X which is in A but not B. And then that means that B is a subset of A minus X. By this proposition up here, if we remove an element, our cardinality decreases by 1. So since A had n plus 1 elements, A minus X has n elements. And then this is where our assumption applies. Here is a set. It has size n. B is a subset of it. And that's exactly what this applies to. So by this assumption, we can say that B is finite and has size less than or equal to n. And that is what we wanted to prove. So the fact that we can talk about sizes of sets allows us proofs by induction. What we can also, or what is also seen, if you were to work through this chapter, is that the operations union and product, the sizes kind of work like you think they should. Well, in the case of union, things are, at least if you were careful about it, things are surprisingly, or you have to be more careful than maybe you think you would need to be. So the first theorem is that if A and B are disjoint, then their union is disjoint finite sets, their union is finite, and the size of the union is the sum of the two sizes. And we can construct an explicit bijection here, but the idea is that since they don't overlap, you have all the things in A and all the things in B, and you need to count those, and so you have the sum of their sizes. And that uses the fact that they're disjoint. What's kind of surprising is if they do overlap, we can still come up with a formula for the size, but it's more complicated. And we get what's called the inclusion-exclusion principle. So if you have any finite sets, then their union has size, the size of A plus the size of B minus the size of the intersection. And one way to prove this is to say A union B, we can break it into two disjoint sets, A union B minus A. And then we have the set we're looking at written as the union of disjoint sets, and we can apply this theorem here. And rewriting the equations that show up, this is what you get. What's kind of interesting is there's another way of thinking about where this formula comes from. So this formula right here. What you can also say is, well, how would you count how many things are in here in the union? Well, first you would say, count the things in A and count the things in B and add those up. But the problem is that if A and B aren't disjoint, if they have something in their intersection, the things that are in both A and B were counted twice. So however many things were counted twice, subtract that many. So those things are only counted once. And that's really where this formula comes from. And that version can help come up with bigger versions of what happens if you union a bunch of finite sets. What size do they have? And if you union 3 sets, you get this long looking formula here, but where it comes from is you have 3 sets, you union them up, how big is that? Well, first add up everything or count how many is in each one and add those up. For each pair, so A1, A2, if you're in both of them, those are counted twice, so you subtract those out. If you're in A2 and A3, you're counted twice, so you subtract those out. And A1 and A3, those are counted twice, so you subtract those out. But then there's a problem. What if you're in all 3? So you were counted 1, 2, 3 times initially. You were counted 1, 2, 3 times here. And so if you're in all three, you're counted 3 times, then you subtract off those 3 times, and then you have to be counted once, is what this last part says. So what is surprising is even just counting finite sets can be kind of complicated, especially unions. What's nice and what we'll not prove is for products, it's exactly the formula that you think. If A and B are finite, their product is finite, and the size of their product is the numerical product of their sizes. And this, again, you can prove by induction. But where things get more complicated is if you want to talk about infinite sets. So we said that a set is denumerable if it is equinumerous to n. So if you're the same size as n, we call you denumerable. If you're the size of n or finite, you're called countable. Countable meaning you can count them, either in the finite case you can stop, or in the denumerable case, you can count 0, 1, 2, 3, 4, and you keep matching them up because that's what the bijection does. So one thing that we haven't done, actually, is we haven't proved that these denumerable sets are actually finite or are actually infinite. But having thought about finite sets a bit, now we can actually do that. And this actually gives a surprising property, and what turns out to be a characterizing property of infinite sets. This says if you have a set A, and you can find a subset which is not the whole thing, but is still equinumerous to the original set, then you had to have been starting with an infinite set. So the proof uses some facts we've talked about, but at least the structure is a proof by contradiction. So assume we have an A, we have a B, which is a subset, not the whole thing, but equinumerous to it. And then for a contradiction, well, we want to prove A is finite, assume that it's not. So assume it's infinite. Or sorry, I think I said those backwards. We want to prove it's infinite, assume it's not, so assume it's finite. But having talked about finite sets, if you are finite, you have some size. And one of the facts that is established in the section on finite sets is if you have a finite set, a subset of it is also finite, and if it's not the whole thing, it's actually smaller. But what we can say is that if A has size n and B has size less than n, then they can't be equinumerous. So for finite sets, you can only have one size. And so A and B can't, we know that they don't have the same size. B actually has fewer things. So we get a contradiction because there can't actually be a bijection between them. So what happened, we made this assumption A was finite. That's wrong. So it means that A is infinite. So what this means is that the natural numbers, we proved that it's equinumerous to the even numbers, the odd numbers, n plus is all the numbers except for 0. So there are a lot of sets you can find inside of N, which are proper subsets, but still denumerable, still equinumerous to N. And so that shows that the natural numbers are infinite. And you can check that because you know the natural numbers are infinite, every denumerable set is infinite, which could be a small proof by contradiction. If it was finite, then it would be equinumerous to some in, one of these sets, 1, 2, and so on up to n. But it's also equinumerous to n, and you can't compose those bijections. So along the way, it is really restrictive trying to always come up with a bijection to the set of natural numbers. So some theorems can be established which say, which let you have some more flexibility in proving that sets are countable or denumerable. So part of what this theorem says is really that these denumerable sets are the smallest kind of infinite set. So one fact which isn't proved is every infinite set has a denumerable subset. So if you are infinite, you can find a subset which has the same size as the natural numbers. And combined with this theorem says if you are denumerable and you have an infinite subset, you are also denumerable. So if you have a set which is the same size as the natural numbers, all of its subsets are either finite or also the same size as the natural numbers. So there's no kind of middle ground between finite and same size as the naturals. What provides even more flexibility is being countable, so denumerable or finite, is equivalent to there's an injection from that set into the natural numbers, or there's a surjection from the natural numbers to A, or A is the empty set. So one way that this can get used is that n times n is also denumerable. So the set of all ordered pairs of two natural numbers has the same size as just all natural numbers. So this is like an infinite grid, the first quadrant of the xy plane, all of the grid points. That has the same size as the natural numbers. And how we can show that is, well, first, it's infinite, sorry. First, we can say it's infinite because it has a set n times 0. So here, these are all the pairs that look like a number times 0. That has the same size as the natural numbers. Sending a number to the pair is the bijection. We can also see that this set is countable by saying take a pair of natural numbers, n times n and m, and send it to the number 2 to the n times 3 to the m. And essentially, well, this is injective essentially because prime factorizations are unique. This function that sends a pair of natural numbers to 2 to the n times 3 to the m, that's 1 to 1, because if you get the same output and assume, say, n2 is bigger than n, greater than or equal to n1, then dividing off 2 to the n2, we can get that 3 to the m1 is this power of 2 times 3 to the m2. But if these numbers are equal, this one is odd, so this one also has to be odd. And the only way for it to be odd is to not have this power of 2, which means n2 minus n1 is 0, so n2 and n1 are equal. But then if you don't have this power of 2, you have 3 to the m1 equals 3 to the m2, and you can see that the exponents then also have to be equal. And so the n's are equal, the m's are equal, so the pairs are equal. So here we're saying because there is an injection from pairs of natural numbers to the natural numbers, and we know it's injection, it's definitely not onto, because it's only, we only get things that have 2s and 3s in their prime factorizations. But because there's an injection, we know that n times n is countable. And we can check that it's not finite. This fact, combined with the theorem about products in the first section, says that if you take any two denumerable sets, their product is denumerable. This can get us an even kind of adding some more surprising facts that the rational numbers are denumerable. So there is a bijection between the natural numbers and the rational numbers, which seems really surprising because the rational numbers, if you plotted them on a number line, are dense. They're all over the place, where natural numbers have these huge gaps in them. But they have the same size. And how we can do that is, first, we know it's infinite because it contains the natural numbers, and the natural numbers are infinite. But what we can do is there's a surjection from the natural numbers or from a countable set to our set. So we can define a function from integers times positive naturals to the rationals, which is saying, given two numbers, form the fraction out of them. This is onto because given any fraction, we can find some pair, which is what makes up the fraction. And so this example says we have some countable set. We have a surjection onto the rationals. So this set must also be countable. In a more explicit way, we can also try to list the positive numbers of the rationals by saying, first, make all the fractions you can that only use numbers up to 1. So that's 1 over 1. Then use the numbers that, or write out the rational numbers that use numbers up to 2. So that's 2 over 1 and 1 over 2. Next up, make all the rationals you can using numbers up to 3. So 3 over 1, 3 over 2, 3 over 3, 2 over 3, and 1 over 3. And then you can say write down all the rational numbers whose biggest number that they use is 4. And so this is generating a list of rational numbers. Every rational number will eventually be on here. And if you write something down in a list, that is really saying that it is countable, because this is the 0th element, this is the 1 element, the 2 element, the 3, the 4, the 5. And so listing them out in this way, and in a way where you know you're covering everything, is really explicitly saying this is the bijection. I'm writing things on a list, and the order in which I write them is the natural number that they get paired. Yeah, so yeah. So a lot of things are countable, and in particular, unioning countable sets gives us more countable sets, or at least or to make that more precise, if we have two countable sets and we union them up, they're countable. So countable means infinite, or this denumerable is countably infinite. What also happens is, so this is another way in which induction kind of shows up. A moderately long proof is needed to prove these facts. If you union two denumerable sets, you get a denumerable set. The proof in here is essentially send A to the even numbers, B to the odd numbers, and that is sending A union B into the natural numbers. So some effort, or we have to carefully check that if we union two sets, which are denumerable or countable, that union is also denumerable or countable. What happens next, though, is we would like to extend this to saying if you union more sets, which are denumerable, like if you union 5 sets are denumerable, the union is also denumerable. And that step is actually a proof by induction. What it looks like is, so the theorem is if you have any denumerable or countable sets A1 up to AN, if you union them, they are again denumerable or countable. What the proof looks like is the base case is when you only have, I guess the most base case is when you only have one. The kind of first base case with some content is when you have two. And checking that the union of two countable sets is countable is exactly what this theorem is doing. The inductive step says if you're unioning up A1 up to AN and then AN plus 1, what you can do is say, well, unioning is associative. So instead of thinking of them as N plus 1 different things, break it into two things, this first part and this second part. The first part right here, that's the inductive assumption. The inductive assumption is assume the theorem is true for N things and try to prove it's also true for N plus 1 things. So you know that this is countable by the inductive assumption. This is countable just from the hypothesis of the theorem. And then you're unioning two countable things together. That's also countable. So this theorem is kind of a standard way that induction gets used. You prove something is true for combining two objects. And then by induction, say if you're combining n objects, the same thing is true. What is maybe kind of surprising, but pretty fundamental, is not only if you union finitely many countable sets, do you get a countable set, but if you have a countable number of countable sets, the union is again countable. This, whatever this is, should not be there. Okay. So this takes some more work. Kind of the idea is if you have your countable sets, you can make up a grid where the first countable set is one vertical column, second countable set, say A1 is your first column, A2 is your second column, A3 is your third column, and so on, where you have countably many columns, and each column is countable. Then what you've done is you've made a grid where you have, which it essentially looks like n times n. You have n columns where you have, and each column has n rows. So you can define a bijection from this grid of laying out all your sets with the natural number. There's the natural numbers times the natural numbers. So this is not the longest proof, but is kind of surprising and but it's in kind of a fundamental fact. If you're talking about countable sets, if you union up countably many, you stay countable. So at this point, the question kind of arises as far as what things aren't countable. We had proved a bunch of explicit bijections between sets of specific sets of the natural numbers. We've come up with a lot more examples, including the rational numbers, n times n. We've seen if you union or product countable sets, you get more countable sets. So at this point, we need to say what sets aren't countable. So there are some rephrasings of some of the facts that we had established before. Really, all of these are essentially contrapositives of facts about countable sets. So if B is a subset of A and B is uncountable, then A is uncountable. This is the contrapositive of if you knew that A was countable, B would also be countable. So the place where uncountable sets show up is the power set. So if you take a set A and then the power set is all of its subsets, what turns out to be true is that those are not equinumerous. And the proof is kind of sneaky. So suppose for a set A that you had a surjection from A to the power set of A. We're going to get a contradiction which says there's no onto function from A to the power set, which in particular means there can't be a bijection. But in fact, we don't even need the injective part. The thing that we focus on is this set B. So the idea here is that this function takes an element and sends it to a subset. That's what this is doing. We don't have a formula for it or anything, but that's what this function is doing. And so if you have an element of A, it's the output of F. The output of A under F is some subset. A question you can ask is, we have an A, we get an F of A, is A in this subset? So F of A is some members of A, is your A in it or not? And so define the set B of all A's which aren't in their subset, which is a little weird sounding, but every A is paired with a subset. You can ask, is the A you started with an element of the subset assigned to it by this function? So we can write down this set B, and then the question is, well, B is a subset of A, and the function is onto, so there is something that gets sent to capital B by F. But then we get a contradiction. Because if we find this little b in our set A that gets sent to this subset, then ask, is that little b a member of this b that we defined? Well, if it isn't there, then b was where, or then little b is in the subset assigned to it by F, which is exactly what can't be happening in B. On the other hand, if this little b we picked isn't in capital B, then that means B isn't in the set assigned to it by F. But that's exactly what has to happen for you to be in this set B. So the problem is that so we can define this set B always. If F is onto, some element of A has to be assigned to this subset, and that can't happen. So this means that the power set gives you a set where there is no bijection with the set A. So in particular, the power set of n is an uncountable set because there is an injection sending a natural number to the singleton n. That's an injection from the natural numbers to the power set. So we know the power set is infinite, but there can't be a bijection. So we know that the power set must actually be uncountable. So what this says is that there are different sizes of infinite sets. There really are. The natural numbers and everything that have that size are kind of the smallest one. The power set of the natural numbers is another bigger infinity. And this is, in fact, another popular size. If you take the collection of all infinite binary sequences, so these are sequences infinitely long that only are made up of zeros and ones, you can show that this is equinumerous to the power set of n. So this is another uncountable set. A proof which is really interesting, but we don't have time for it, is that the interval 0, 1 is also uncountable. So that means that all of those sets, all of those intervals of real numbers, those are all uncountable sets. A question which is really interesting and the resolution of which is very complicated is, are there any sets in between? We know that there's kind of the natural numbers and things that are countable. There's things that are the size of the real numbers. And in fact, these two examples are also the same size as the real numbers. You can ask, is there anything in between? And the answer is, it depends. And exactly what it depends means is a very complicated question. The last thing I want to say is that there's an important theorem, which is often a highlight of this type of proofs class, called the Cantor-Bernstein theorem, which says that almost being equinumerous is antisymmetric. So the theorem says if you have an injection from A to B and another one from B to A, then A is equinumerous to B, which is really surprising because it says if you have two injections going both directions, then there's actually a bijection between the two sets. And it's not at all clear where the bijection comes from. That's kind of what makes the proof difficult, but that is really useful because we can say that we had been talking about just open intervals are all equinumerous to each other, but in fact, every interval, no matter the endpoints, are equinumerous to each other. And the proof, if you use this Cantor-Bernstein theorem, is not difficult because all the work is stuffed into here. So these two sets, there's a bijection. We won't come up with one, but we can say the open interval is a subset of the half-closed one. So that's an injection. Just send it to itself. But also the open interval, or the half-closed interval, is equinumerous to this half-closed interval. And that is a subset of 0, 1, which means there's a bijection from the half-closed interval into the open interval. And so because there's an injection from one set to the other and a different injection back, those sets are actually equinumerous. So this was an incredibly brisk romp through this chapter 8. This stuff, like I said, won't be on the exam. It will be on some of the extra credit assignments. The proofs there are all fairly short, and a lot of it uses what we already know about functions. So we've talked a lot about injections and bijections and composing them. And so the extra credit will take kind of assimilating what we already know with some of these new concepts that we've introduced. But in addition to that extra credit, there's going to be some extra credit built into the final exam as well. So with that, I guess we'll wrap up today. Hopefully you have an appreciation for what the non-computational part of mathematics looks like. This semester was not ideal, but hopefully you enjoyed parts of it. And good luck with the final and the rest of your finals. For office hours for the rest of the week, I'm keeping my normal office hours today and tomorrow, but on Thursday and Friday, I'll just be diligently monitoring my email. So let me know if you have any questions. If you want to set up a Zoom meeting, we can do that. On Thursday and Friday, I don't have really other obligations, so I should be pretty responsive. But other than that, good luck. I enjoyed teaching this class. Hopefully you enjoyed taking it a little bit. And watch out for the final to get posted this afternoon. All right, so I can stick